on this computer. Okay. Good morning. First of all, I wanted to prove to you that the cats and dogs will actually work. So this morning I took a picture of my dog. This is my dog. His name is Ken Jr. Huh? I'm not sure. Thank you for reminding me. I always forget. Okay. So this is my dog. Cute, huh? So so what we can do, we can download this. Okay. Now it's in this. This it? Where is it? Download. Didn't work. Let me see. Let me try again. Download. Download. There it is. Okay. The image 2054. So I'm going to cut. And then I'm going to come down here. Courses. Lectures. Cats and dogs. I'm going to paste it into this folder. Then I'm going to come back. And by the way, you see here we input the name of the file into the source code. It's not good. My professor in college would get angry at me if I did this. But we're in a hurry. Later this afternoon, I'll show you how to not do this. So that was cats and dogs, image 254. Okay. Should use the command line. Okay. So I've never tested this, so I don't know if it's going to work. So here it is. Yeah. So that's AI for you. One thing, I'm not sure how did we train this final model? Let me just check here. We trained final model. Yeah, we did use BGG. Okay. So one thing I was thinking, maybe that because this image is I say portrait. So when it resizes to 224, it has to stretch. So maybe if we made this a square, cut out a square, maybe it would work better. But that is homework assignment for you. I don't know if it will work. Why didn't it work? Okay. That failed miserably. So let's go on. Today I wanted to talk about super resolution. So super resolution. I think this is a very, until now we've been talking a lot about classification, but a whole nother branch of AI is a super resolution. So what is super resolution? So normally when we have a small image and we want to blow it up onto a widescreen TV, we use this method called a bicubic. Okay, so this is the kind of gold standard, which I'll talk about a little bit later. And these other methods, regression, and in this paper, the reference, this is a super resolution here. So let's see. So normally interpolation, the simplest is just the nearest neighbor, which is just blow up the pixels. That were many. But bilinear is a little bit better. And then a bicubic uses a 4x4 square of pixels to interpolate. So this graph kind of gives you an idea difference between a nearest neighbor bilinear and bicubic. Hopefully. Down here. Okay. So a peak signal to noise ratio is used. It's kind of hard to see in this image, but this original image, and then the quality is going down here. So you see the PSNR score going down here. So this image is supposedly less quality than this image, but it's kind of hard to see on this screen. So how to compute the PSNR? First, compute the mean squared error. So this is actually very simple. If you have the original image and the noisy image K, then just subtract each pixel and square the difference and sum that up and compute the average. So it's literally the mean square error. Okay, but usually they report PSNR, which is just this mathematical function here. Okay, and if you're using Python, you can use something like this, PSNR. So super resolution, the aim is to recover high resolution from a single low resolution image. Okay, so if you have a low res image like this, you want to feed this into your convolution neural network, and you want to get a high resolution image like this. So I think one misconception people have, I once had a student, he asked me, well, I have all these low res images, and I want to make a super resolution images. I said, well, do you have any high resolution images? He said, no. So I told him, well, it's not possible to create a super resolution image if you have no high resolution images to train with. Okay, so it's not magic, it's statistics. Okay, so especially medical images. Medical images are often very similar. Okay, so you can train a network to kind of guess what the high resolution image should look like given a low resolution image. Okay, but medical images are always very similar. So that helps. Okay, so so if we want to train a network, so if we say we have these high resolution images, we have a bunch of them, then what we can do is we can degrade and kind of simulate the low resolution image. Okay, so that's usually how you start with super resolution. So then we train, so we take the low res image that we generated, feed that into our network. This is called feed forward. Okay, and the network will generate a high resolution image. Okay, but we have the high resolution image that we started with. This low resolution image was generated from this high resolution image. So we know what it should be. The answer should be this. So we can compute our PSNR and use that for a backprop to adjust the weights in our network. And then we rinse and repeat. So if we do this over and over and over with thousands of images, then the network will gradually learn how to generate high resolution images. Okay, so this is from a Japanese book. It has a very simple, this is a very, probably the most simple network that you could create is from this book here. But don't worry, you don't have to learn Japanese too. But if we translate that into Keras, looks something like this. We see we have the image input. We just have 3 convolution layers. The first layer has 64, then 32, and then 1. Okay, so the thing about this is the final output. Notice that we don't have a sigmoid function here. Before, when we were doing binary classification, the final layer had a sigmoid, but here the final layer is just another convolution. So this is going to output an image. Okay, so everything else should be pretty much the same. Okay, and by the way, this is called the I think call it the function method. Instead of using the sequential and add, they use this. I forgot what they call this method. It's another method to define the network. It uses X. Here you see the input to this. The second layer is an output from the first layer. Okay, so basically the same thing. And finally, the model can create in one statement like this. Okay, so this is what it looks like. It's very light. It's only 8,000 parameters, which is good. And we can see it trains pretty well. So this looks very good, promising. Okay, so PSNR 35. So, and it's also trained very fast, only 1 second per epoch. I don't remember if this was on the Jeep. I think this was on this. Well, anyway, doesn't matter. But it's very light, easy to train. But we can do a little bit better. This is called a DD super resolution convolution neural network. I forgot what DD stands for. But it's a little more complicated. Actually, it's quite a lot more complicated. But I think, yeah, I think this is what they call a UNet. You'll hear this UNet a lot. So what is a UNet? You see these, it kind of shrinks the image down and then it builds it back up. So it kind of make a U. And then the layers are connected. They have this connection here. Okay, so that's why we can't do a normal sequential method to define the model. We have to use this, I forget they call it functional method, but you see this output from down one is going to be used as an input later on. So it's a kind of a complicated, but just assume that this is going to work. So now we have over 1 million parameters, so a little bit more heavy. And we get something like this. And so we've improved to 37 PSNR. But now it takes about 5 times as long to train. But still not bad. Okay, so if you're interested in pursuing, if you're interested, I have the code here and some sample data. You can see for example, these are the high resolution images. Okay, this is 1080 images. And I have a script to generate the low. These are the low resolution. This is 256. Okay. So if you're interested, feel free to the main Pi and utilities, and the PSNR code is here. And so besides super resolution, it's very related to noise reduction. So it's basically the same problem. If you have a noisy image and you want to make a denoised image, you can use almost exactly the same method, except that the resolution stays constant. But and in for medical imaging, we have a lot of problem with patients getting radiation from CT or PET. So there's a lot of research in low dose imaging. So for example, this ultra low dose PET CT. Okay, this is a paper written by a guy at Stanford University, and he came here. This guy Greg Zarchuk at Stanford University. He's a medical doctor. So basically, what he does or did, okay, so this is another UNet you see here. Okay, so it's more complicated than the one that we saw. Okay, but basically the same idea. Take a low res image and produce a high res or a denoise. It's actually a denoising. So this is with a PET, but PET CT, or is that it? PET. I'll come down here to the results. Excuse me, PET MRI. Okay, so nowadays they have all these PET CT and PET MRI and proton MRI and all these combination modalities. Okay, so you can while you're taking the PET image, you give a what do you call injection of a radioisotope. So while that's going on, you're also taking an MRI image. Okay, so you can combine the two of them. So the idea of this paper is this is the MRI, and this is a normal PET image. Okay, but you can do a low dose PET. Okay, you can do a low dose PET, but here he did a oh yeah. So how do you generate? So you have a bunch of examples of normal dose PET images. Okay, and the PET image is created from there's a list of they call incidents. It's every time a what's it called, a positron or something, quantum mechanics happens, and they have this list of these. They have a ring detector and all these incidents. Okay, so they reconstruct the image from that list. Okay, but it's easy to simulate a low dose image just using a 1/100th. Use just 1% of the incidence list. Okay. So if you were doing normal super resolution, maybe you could use a half a resolution, or maybe at most a 10% or 10% dose. Give the patient 10% dose, and maybe it could reconstruct the normal dose image. Okay, but in this paper, he's doing 1/100th. Okay, only 1% of the imaging dose to the patient, and you see a normal. It's not possible with using super resolution alone. So this paper, they combine the information with the MRI. So if you input both the MRI image and the MRI image plus the low dose PET image, then you can generate a normal dose PET image. So this kind of low dose imaging is important, especially if you're dealing with children. Most of our patients are maybe in their 70s. It's not such a big issue because you assume that they're probably not going to live another 30 years. But when you're dealing with children, you want to be extra cautious of a dose. So anytime a doctor prescribes a PET image or a CT image or any kind of X-ray image, they're always very cautious with children. Okay, so I think this is a very positive, good application for AI, low dose imaging. But the problem is that you have to convince the doctors to trust it. And most doctors will say, well, if the patient's life, if we were just generating super resolution images for a Hollywood movie, that's fine. But this is for real patients. Okay, so most doctors, I think it's good they're skeptical. Okay, but so what Greg was saying that you can show statistically that the low dose image is just as good as a normal dose image. Okay, so and besides, who said that the normal dose image is a gold standard? It's just that what you're used to using all the time. Okay, so I think low dose imaging is a very promising field in AI. Okay. And I just wanted to mention one more. Yesterday, David mention segmentation. And that reminded me, this is another good application for AI, is segmentation. So, so this is another research from Stanford we visited last year. So, so I just wanted to mention that this UNet, again, is very popular. The same idea. They start with a high resolution, and you shrink it to a low resolution, and then you build it back up, and then there are connections in between here. So same architecture. And this paper, I forgot. They're trying to segment. So here she used the example of the jawbone. So can you make a? Yesterday we saw the image of the elephant, and first we located the elephant with a bounding box, and then we made a mat. It's called a mask. Okay, so this is what they call segmentation here. Okay, so I won't go into detail here, but this is a dice similarity score. So this is often used in papers. And the results. Okay. So the last topic for this course is GANs. So GANs are very popular now. So G stands for generative. A is for adversarial. And it's for networks, right? So this is taken from wait. I have the recording on here. Clear recording. Okay. Okay, so one of those books that you have is covers this GANs here by Jason. Right, so generative for Python. Okay, so yeah, I thought it would be instructable to actually go through, especially the first couple chapters. Let's see here. In chapter 6. All right. So this just, if you have your plots, can you see your plots today? Yeah. Okay, so we start off very simple. Okay, let me close this. Close this. Close this. Let's see. I don't remember. I have spider. I don't remember one slides. Okay, I'll go through some of these slides first. Again, so one thing you can do with GANs is from a photograph, you can generate an image that's in the style of Monet or Van Gogh. Okay, so this is a very popular. There are websites you can upload your own photo, and it will generate something looks like Monet. Or this is an example we'll see later. Zebras. So if you wanted, say, for a Hollywood movie, you didn't want zebras, you wanted horses. So you can convert back and forth between horses and zebras. Okay. So this is a website. You can upload your own images. And for medical images, so it's not only for Hollywood, but for medical images, they use GANs a lot recently. Let's skip over this one. This was a student, one of our students here. Is it? Oh, maybe not. Oh, sorry. This is from Stanford. I forgot. Anyway. Oh, this is one. Nomura-san. Nomura was a student here. Okay. So basically what we have, again, so it's a adversarial. Okay, so it's kind of like a game. You have you have to train two networks. One is called the generator, and one is called the discriminator. Okay, so the generator will take generate some random image. Okay, maybe it looks like this. Okay, so the discriminator, his job is to takes an input, but it has to discriminate. Is this a real sample? Is this a real Monet painting, or is it a what do you call a forgery, right? The discriminator is trained. So we feed it first. We give it a real Monet, and we have a label. Okay, label is 1. It's real. Okay, so if it makes a mistake, the discriminator will go back and adjust its weights. Okay, so this is a real Monet. Okay, but the generator will generate a fake Monet. Okay, but the discriminator has to determine. So if the output, if the discriminator guessed correctly, said, "Oh, this is a fake," okay, then the generator has to update its network to say, "Oh, I didn't make a realistic Monet painting. I need to adjust my weights somehow." Okay, so this goes on in a loop over and over, and eventually the discriminator will have more and more difficulty telling, is this a real painting or is it a fake? Okay, that's basically how it goes in a loop like this. But when you're finished training, you don't need the discriminator anymore. You only need the generator is what you're interested in. Okay, so you save that to an H5 file, and then you can use that to generate random Monet paintings. Okay, that is basically how it works. Okay, but I think I'll come back to this later. This slide. Okay, so I want to come back. So how do, in practice, it's one thing to just kind of wave your hand and this course is about actually making a real working example, real code that actually works. Okay, so this is, we start off with a very simple example. So this is just a parabola, right? So our task is to create a GAN for the parabola here. Okay, so the next example, it generate. Okay, so this, what is this? This sample number 2 here just generates samples based on this formula x squared generate. Right, this is the formula here. Oops, what happened? Convert string. Oh, sorry. Okay, so this yeah, maybe I should what's the book? The book. Basically what I'm doing here is your list of books here. Generative advertising. So I got all this from here. And I think 6. Yeah. So starting in chapter 6 here, that's what we're doing here. And we're going to make a plot like this. This is our function. We did that. And then we're going to, first we're going to define a discriminator. Okay. So the next step, define a discriminator. Okay. By the way, we're supposed to go up till 10:15. Is that right? Yeah. Okay, if you need to go, you can just go. I'll just go on recording. Okay. So this just defines a very simple model here. Okay, the model is just a fully connected network. Remember, for classification, you always see this dense here, okay? And the output is a 1 neuron with sigmoid. Okay, so this is, remember, this is a discriminator. So it's a yes, no, real or fake, okay? So this is a very simple discriminator. So the next step is number 4, fit the discriminator. Okay, so we come down and we're going to train the discriminator with random data. Okay, you see it starts off at about 50%, but hopefully this, we'll see it go up. I'm going to do 1,000 of these epochs. Okay, so I'm going to stop this and go back to my PDF here and go down. Okay, so we did this discriminator, did this. This is what it looks like. Okay. So we have 2 functions here. We have generate real samples, which are use the formula, and then we have generate fake samples, which are just random numbers. Okay, it's kind of like I showed you yesterday. I made a real samples that are curve shape, and I had another just fake, just random number. So this is a good method to first step of training. Okay, then we're going to train the discriminator. So many epochs. Okay, So if you let that run, you can see, I forgot the left, and the left number is the real. Okay, so when you gave it a real, these two numbers here, this is the epoch number, and then the second number here is when we gave it a real sample. Okay, it's guessing 100% of the time it's getting correct. Okay, but then when we gave it random numbers, okay, it's getting maybe close to 90%. It's not very stable, but it's getting pretty good. Okay, so real and fake updates the model, then evaluates the model, same example. Okay, so maybe around 80–90% accuracy. Okay, so that is our discriminator. So what about our generator? So let's look at this. Oh yeah, why don't we just scroll down here. Okay, so we input. Okay, so this is where they talk about latent space. So this is kind of confusing. I think of latent space as, just think of it like a random number seed. Okay, what is a random number seed? It's just a number. If you input it into your random number generator, it will output another number, right? It's always the same. It's not really random. It's always it's a mathematical function. Okay, so it's determined. So latent, I think of latent space as just a vector of random number seeds. Okay, so if for example, for a Monet painting, a single random number seed is not going to be enough, because a Monet painting is very complicated. So you need a more complicated random number seed. So the way I like to think about it is like that. Okay, but for this case, the latent space is going to be the input, and the output is going to be this parabola. Okay. So by the way, the first example here is you think this is a really stupid way to make a parabola, but try not to think about that and just think about the structure of the generator and the discriminator. Okay, that's what the aim of this sample is. Okay, so we're going to find the generator here, and we're going to come down. Oh yeah, so the generator, you see it's very similar to the discriminator, is that it's just a dense network here. Okay, and the output is going to be, right, so the output is just a number. That's why the activation now is just a linear, I think it's just the value for the one neuron. Okay, it's not sigmoid now. It's just the value. So we're just going to get a value, which it should be close to x squared. Okay. So now he just chose a 5 here as the latent space. Okay, so they're going to vector with a 5 floating point values. It's going to be the input to this generator, and it's going to output a number. Okay. So then you come down, and this is generate the latent points. Okay, so this just generates random numbers. Okay. And then fake samples. Okay, so these are for the fakes. Same. Tying all together, we have the complete list. Okay, so these are just random numbers here. Okay, so beginning, so we start to train the generator. Okay. Okay. So here is, okay, so this is the GAN, define the GAN. Okay, this makes the complete GAN here. So we add, we start off the same way you usually start off the sequential model. We're going to add the generator, and then we're going to add the discriminator. But kind of the trick here is this line here. Okay, so this if you didn't have this, it would train, I think it would train the discriminator twice. Okay, so this is kind of a tricky, if you didn't read this book, you would never figure this out. Okay, then we're going to use this train on batch, which is the same as a train, but we're going to loop the number of epochs. Okay, so discriminator looks like this. Okay, the output is sigmoid. It's just a yes, no. This is a real or fake. The generator is here. The output is linear because it's just a number. Okay. Defined again. Okay, this puts the generator discriminator connects them together. And then our main loop is like this. So if we run this, let's see what happens. Fit the discriminator. Okay, used. Okay, so let's skip down. Complete example. See if this works. I forgot how long this will take. We did 10,000 epoch. Okay, so this is going to take some time. I'm going to stop this here. At least we know it works. Oops. Okay, so if we were patient and we waited for that to finish, we would get something like complete again. Okay, it gets output like this. And then we start, I think the red is the real examples. And this is after 2,000 epochs. Okay, it's not very good, but it's not completely random. Okay, but if we keep going after, this is after 10,000, it looks pretty good. It's getting close to what our real function is. Okay, so again, this is a very crazy way to generate a parabola. But the point is how to create a GAN, create a network. Okay. Okay, so they go on more interesting examples. The same structure of the GAN is the same, but we start getting more interesting examples. So, for example, we we've seen before, the numbers. Okay, so in this example, we're not classifying the numbers, but we want to generate random numbers that look sort of like real numbers. Okay, so the discriminator is the same. Is this a real number from MNIST, or is this some fake number? Okay, so the discriminator has to decide. Okay, so if we come down here, down. I'm sorry, I haven't had time to make a PowerPoint slides yet, but you can see at first the generator is just generating a random noise. Okay, so it's easy. So at first the discriminator has an easy job discriminating between the fake and the real. Okay, so train the generator down. Okay, so now they're getting a little closer. Still not very good, but this is after only 10 epochs. They look sort of something like numbers. Okay, if we keep going after 40 epochs, getting a little closer. And after 100 epochs. Okay. So you're wondering, why would anyone want to do one thing, one application for GANs is we're talking before about data augmentation. So especially medical images, you never have enough images, especially for a rare disease. Okay, you have lots of negative samples, sort of disease-free patients, but if it's a very rare disease, you only have a few, images of a patient. So one application for a GAN is to use a GAN to actually generate your augmented data. So it can generate more than just shifting and rotating and zooming. You can generate random images that hopefully look something like a patient with a real disease. Okay. Okay. So come down. These are generated. Right. Okay. So the next gets a little more interesting. So what about photographs? So yesterday we saw this, what's it called? CFAR, these photographs. Okay, so this chapter does exactly the same thing, but using a little more interesting images. Okay, so the steps are all the same. Come down. Come down. So at first, at the beginning, it just makes a random grayscale images, the generator. So we have to retrain the generator. So you start getting, after just 10 epochs, you get things that sort of look like images. But if we keep going, start looking kind of real. After 90 epochs, they almost look like real images. Okay. This one was after 100 epochs. This one, 200. Okay. One thing about these GANs is that there's no right or wrong answer. So you know, if you look at one of these images, you never know when to stop. Okay, you could go 200 epochs, you could keep going about 2,000 epochs, right? But it's really up to the human to decide. Okay, these look kind of good. You know, it's kind of there's no right or wrong answer. Is this a CFAR image? Is this if you know noise? Okay. Okay, so what's this? These are more CFAR images. Okay, so he input a single vector and generated. Okay. So then we can do the same thing with faces, right? So these faces are not real people. They're generated from what I said, the latent space. Okay, just think of it as a random number generator, and it will generate a face that looks something that's been trained on many real faces, but they're not real faces. So you can the vector is just think of it as a big number. So you can interpolate from one face to another and have it make a kind of cool looking called a morphing from one face to another. But remember, this is not a real person. It's just a randomly generated face, and this is another randomly generated face. Okay, so then you can morph in between two. Okay, so we have this database. These are a real celebrity faces that we use to train. So, by the way, this is kind of a ethical issue now. That if you use a celebrity face, say, to train your network, do you have to give credit, or do you have to pay them for the use of their face? Which I think, yeah, you should, if you're going to use their work. Okay. So we come down. And we come down. Okay. So after these are generated faces. Latent space. Okay. These are more randomly generated faces. Some of them look pretty bad. Some of them look pretty real. No. Okay. Interpolate between two faces. Yeah. So this is a morphing. Morphing. Okay. That was one latent space. Okay. Generated faces. Okay. Okay, so that's faces. So failure modes. I'm going to skip over this chapter. This is sometimes you can get into trouble using GANs, but it's too hard to explain without any images. You can kind of trick it. You can trick the GAN into thinking that this is a real Monet picture, even though it's not at all. Okay. So if you're interested, you can go back and read this chapter. I want to skip down to part 3. Okay. How to evaluate. Okay, this is not what I wanted. Let's go back to these slides. Supervised, right? So this is an example of unsupervised. Okay, I think I have a, oh no. Okay, in normal supervised training, you have a label. Okay, so this is a dog. Okay, so the label is a 0, and this is a cat. The label is a 1. That's called a supervised training. But here, for example, if we had a long list of, for example, if we want to convert from zebras to horses, okay, we have a bunch of samples of zebras, and we have a bunch of samples of horses. I'll go back. Okay, on this image, right? We collect, 1,000 zebras, and we collect 1,000 horses. But this image of the horse does not exist. You cannot say that this is a correct image. It was generated from the zebra. And likewise, the horse, this zebra never existed. Okay, so you cannot say that this is the correct, zebra image. All you can do is do this kind of game where you try to trick the discriminator and go back and forth. Okay, so that's the difference between a supervised and unsupervised training. Okay, so if we go down, supervised versus unsupervised, there's no correction. Okay, discriminator, the generator model, to input some a vector. It's just a numbers, and somehow it generates a beautiful painting. And the discriminator has to decide, is this a real or a forgery? Okay, so, all right. I did these slides, we've seen all this. Okay. Seeing this. Sorry. Review. Okay. I forgot I had all these slides. Okay. Go down. Okay. Numbers. ReLU. We already talked about this, ReLU. Leaky. Oh yeah. So one thing about GAN networks, for some reason they use this what's called a leaky ReLU. Okay, so a regular ReLU looks like this. It just takes the if the value is positive, just output the value. If it's negative, output is 0. But a leaky ReLU is the same. If it's positive, it's the same. But if it's negative, you're going to multiply it by this alpha. Okay. So why they use this in GANs and not other networks, no one seems to know. They just say that it's best practice. Best practice just means that from experience, many researchers around the world have found that leaky ReLU works better in GAN networks. So don't ask me why, but you'll see in the network leaky ReLU. Yeah, here you see this leaky ReLU. Okay, and then the alpha is 0.2. Okay, so that means that if it's negative, you're going to multiply the negative value by a 0.2. So I have, no one seems to know why alpha is 0.2. It's just one of those hyperparameters. Okay, so what was this? This is a generator, right? And then we start off. Right. Okay, see this for small photographs. Okay, I'll just skim over this. Faces we've seen. Okay, so this is where how you linear interpolate from one face to another. Okay. So until now, we've been using this latent space, which is, to me, it's kind of strange. But this pixel is called a pix to pixel. So we're going to interpolate from one image to another. So this is more what we're talking about, from a photograph to a Monet kind of example. But here they use from satellite images to Google Map images. Okay. So this example, we have a bunch of, with Google Maps, you can switch between satellite view and map view. Okay, so if you accumulate a bunch of those, you can train a network to interpolate or kind of guess if you input the map, if you input the satellite image, the map would look something like this. But note that this is not really a map. This is not a real map. Okay, a real map is not. It's not a simple bitmap. Okay, a real map has overlays. It has the latitude and longitude at this point, and a bunch of those, and it builds up the map. But this image is just a bitmap that kind of looks something like a Google map. Okay, so this is kind of not a real practical example, but just the fact that you can do it is good training exercise. Okay, so CycleGAN. This is a popular CycleGAN. So this CycleGAN is where I was saying horses and zebras. So we have one folder with full of thousand. I think. Oh yeah. Okay, so you have one folder had horses and one folder with zebras. Okay, so this is what I was saying, unsupervised training. So you can imagine this example like if you wanted to interpolate between a hand-drawn shoe and a real shoe. Okay, you could use this method if you have a bunch of real photographs of shoes, and you could use this. It's called an unsupervised method. Okay, so this we input first GAN generator a zebra. Okay, so I told you that a GAN consists of two models, right? It has a generator and a discriminator. And here in CycleGAN, we're going to train two GAN networks. So we're getting really big This is like big data. You need a supercomputer to actually do this. It's not going to run on a notebook computer. But anyway, the second generator, right? So so like I say, we don't have a before we knew this is a fake Monet and this is a real Monet. So we had a label, but now we don't have any labels at all. We just have horses and zebras. Okay, but what we can do is the GAN number 2 here. It's going to I say do the reverse, convert a zebra back into a horse, and then we do know if a real horse or a generated horse. So we have a label that we can train, something that we can train on, something like that. Okay, so this is horses on the top row, and then translated. So on the bottom row, it tried to turn the horses into zebras here. This was after 53,000 iterations. So it takes a very long time to train like this. So you need a very fast GPU. So here we have what top is zebras. So these are real zebras on the top. And then horses, tried to turn them into horses at the bottom. Okay. So we can go back. So I think this is why they call it cycle GAN, is that we take a real image, we generate it, and then reconstruct. So we go in a kind of loop back and forth. Here. Okay, so if you're interested, right? So so this is a Amazon Web Service. If you're really serious about training on large data sets, you need a big supercomputer. So one option is with Amazon, but if you have some budget from your lab, then maybe you can subscribe. Okay. This I talked about last time. This was papers with code. We talked about yesterday. Yeah, function models. Normally, this is what I'm saying. Normally, we start with a sequential, and then we add layers like this. But this functional method is more flexible. Okay, so we can start with an input layer and a dense layer, and then we can add them into this model like this. So this functional method is more flexible. If you want connections, like a unit has connections between layers. Multiple input as well as models that share, they can share layers and have all kinds of crazy ad hoc networks. So unit, yeah. Here. Upsampling. Yeah. I forgot. Generate basis. Okay. Now it's 10 o'clock. Do you have any questions about GAN and networks? Understand it all? I know a lot of information. So do you need to go? It's 10 o'clock now. Okay. It's fine. It's fine. You can go. I'll just I'll keep talking until 10:15. Okay, so so just feel free to go. Um I'll keep because we're still recording. I'm just going to keep plowing ahead. So the next topic I wanted to discuss was pop quiz, right? Pop quiz. So this is so if you are taking a real course, you would get a quizzes, Keras quizzes. I can't find it. Is it? This is it. Yeah. Okay, so this is a final examination here. You okay. Perceptron can only be used to classify linear separable data. Okay, so I didn't go into a lot of theory, but I think I forgot. Linear separable data. I don't remember. True or false? I don't remember. Sigmoid, ReLU are okay, I know this one. This is activation functions. Okay. So select all correct statements for Python Keras. Keras can only be used with TensorFlow as a backend. So this is false, I know, because used to have this backend called Theano, right? But it's kind of old-fashioned now. Keras can run on CPU and GPU, so this is true. Keras supports multiple backends, right? Here's Theano. CNTK, I've never used this. I don't know. Considering the following image representation. The above represents selects all true statements. The image is represented in the form of width times height times 1. Yeah, okay. It's not RGB. Kind of hard to see here. I want to control plus. See a little better. One. Is 1 byte or one. The number of a array indicates how black or black are the pixels. Yeah, that seems reasonable. Consider the following fully connected neural network. Okay. The network above, the network has one hidden layer. Okay. So this is kind of a trick question. I think I think of this as an input layer, a hidden layer, and output layer. So I would say yes, but I think the correct answer is actually no. Depends on how you define a hidden layer. The output of the network, well, it depends on the input.
I think the input layer is supposed to be the image.
Right, yeah, right. So this actually has two hidden layers, right? So this is kind of a trick question, I think. Every time I get it wrong. This is a required, the output of the network is in the form of 10 different probabilities. Right, so the output, well, if they use softmax, assuming that they apply a softmax, then I think this is true. The input is width times height and size. Yeah. Okay, so this is where they use a flatten layer to take to copy all the rows onto all the together and make one flat image. Okay. So given a set of images, we are able to perform data set augmentation as shown here. Make all the correct statements. Augmentation is useful in cases where there are few data. Yeah. Augmentation allows neural networks to generalize better. That's true. Augmentation cannot be used on large images. That is not true, I would say. So consider the following VGG16. The VGG16 network shown above is highly suited for image classification. So yeah, VGG16 is what it's used for. We can often reuse the convolutional part of a CNN and then train our own dense. Yeah, right. So this is what transfer learning. Okay, so with transfer learning, you keep all the convolution layers and only these blue fully connected layer. You only have to train the classification part. So that is called transfer learning. Convolution neural networks cannot be used for text problem. I think this is actually false because you can have a 1D convolution network that works on signals rather than images. So consider this text phrases, this text representation. Okay. In this representation, we only keep the most common words, the ones in bold. Common. Is that true? I guess so. Words are represented as dimension and documents as vectors. Yeah, so this is the bag of words method. The documents are vectors. And the more words in your vocabulary you have, the more dimensions you have. The words are represented as vectors. So this is called the embedded. So I think what they're showing here is a bag of words. I hope. Okay, so considering the following text embedding. Which of the following statements is true? Words are represented as dimensions. I think words are represented as vectors in embeddings methods. Semantically, similar documents are expected to be near one another. That's true. Remember, like a king and queen should be near each other. These representations can only be used in recurrent networks. I would say normally they're used. Usually when you see which of the following statements is correct? Only one of these is correct. Okay, right. So I would say if we can only choose one, I would guess maybe this one. What do you think, David? Do you know the answer to this one?
I don't know the answer, but I'm assuming you can use it with other networks because it'd be strange if it's only usable with a single design, right?
Do you think it can only be used with recurrent neural
Oh, wait,
networks?
it's only one answer is possible.
Yeah.
Then I think it's got to be the middle one, right?
Yeah, that's what I guess. Usually when I see this word only, I raise a red flag.
Yeah,
Can only be. Okay, let's try. So this is what the showed yesterday this LSTM, right?
Hmm.
LSTM, yeah, we saw this yesterday. LSTM cannot be used with sequential data. I'm guessing that this is false. And this is definitely true, or a category of RNNs. Apparently there's some trouble with RNNs. They're difficult to train. So they use LSTMs. But I've never been able to wrap my brain around this diagram. Okay, just take your word for it. Okay, Mark, now we're getting really into the theories. These questions gradually get harder and harder.
That's reinforcement learning, isn't it? The left side.
Is it? I don't know. Select the correct formula. An agent is situated in an environment. The environment has different states, and the agent performs actions and receive rewards.
I think it's the agent situation. The agent selects the preferred state for each one. I think it's the first one.
Okay, I'll take your word for it. Whenever I see things like Markov is like my brain starts to melt.
Yeah, I'm also every time I have to reread Markov, I cannot remember it for the life of me. Indicates how fast the algorithm will learn using an e-greedy strategy.
Yeah, I think
the second one I think is wrong because epsilon greedy means it also uses randoms. It's yeah, the third one is correct for sure.
The learning rate indicates how fast. So I think this is true.
The third one is true, and the first one, learning rate alpha. I don't know if it's how fast. It's kind of like this. I think it's similar to the gradient descent to step size, but I guess it probably. I think
I think
alpha
it's true.
more does alpha means more how impactful each action is. I think to the learning, but we can.
Yeah.
I think it's not definitely wrong.
Yeah. I think it's true. I'll put my reputation on it. Consider the source code for training a deep neural network in Keras. Yeah, I hate these kind of questions. Is it correct? There might be some tiny little missing a comma here. Is it true? I don't know. It looks good to me. Is the above code correct? Without being able to copy and paste it and run it,
nothing sticks out.
One thing, the activation is softmax with number of classes. So this looks good. And then the loss function is categorical. Okay, if this were binary, I've made this mistake before. I had a binary with a softmax. RMS prop. Okay, so yeah, it looks good to me. I don't know. So is the above code correct? So maybe
I don't know embedding or LSTM. It's LSTM seems strange to just add LSTM.
Yeah.
But is that how you could? Is that like a fancy way or a quick way of doing transfer learning?
No, it's like we were doing yesterday with language models. So if you use the embedding, embedding means that one word, each word is assigned a vector. And that's about, so I don't know, if you're doing if this is a classification, then I don't know, looks pretty good to me. Probably wrong, something wrong with it. Okay, consider the code training a neural network. Let's assume.
Consider this for reinforcement learning in Keras. Consulted. Oh God, what is all this P rel? Didn't spec base size. Input shape base size, that makes sense. And the output shape should be number of actions, but PR value. Let's assume this in
Okay, in order to complete the command. Okay, so
the dense for sure. And I think LSTM makes no sense because yeah, it's got to be the last one because the output has to be the number of actions.
yeah, okay. Yeah, that makes sense. Okay, so let's take a 15-minute break, and when we come back, we'll check our answers. So I'll see you at 10:30.
All right.